I'm going to talk basically about pattern formation and how to control the development of patterns and a few kind of prototypical problems.
During the Julian Cole Lecture at the 2014 SIAM Annual Meeting, John Lowengrub described the mathematics of the micro and macroscopic interactions that occur in the formation of liquids, solids, and even biological tissues, and how controlling these interfaces could have benefits in applications including oil mining, metallurgy, and medicine.
You have two parallel plates and you have a viscous fluid in between, and you pump fluid into the center.
In oil recovery, you pump water and try to displace the oil and collect the oil in wells. The problem is that because you have a less viscous fluid displacing a more viscous fluid, what tends to happen is the fluid fingers, and so it's not very efficient at displacing the oil. The oil gets caught in the wells. And so one of the interesting questions is, how can you stabilize it? And so what our work showed is that you can stabilize it with a very simple mechanism, which is taking into account that what's driving the fingering is an imbalance between the driving force of injecting the water into the oil. And so by doing it so that the destabilizing force, which is the injection, balances the stabilizing force, which is surface tension, one can then control the shape.
Crystal growth, which has numerous applications in modern technology, is another field where controlling shape and formation is desirable.
Even though fundamentally they're very different physics, mathematically the equations are very similar. And so the same techniques that we use to control the shapes of these less viscous fluid displacing the more viscous fluid works exactly for how you can control the shape of a growing crystal.
Lowengrub also described how controlling the physical interactions that occur during the formation of metallic alloys might be used to produce stronger metals.
In an alloy, you have multiple components of materials, and typically what happens is that the second phase, or the less abundant material, will form precipitates, and these precipitates can have dendritic shapes. And those dendritic shapes, if you have too much of that, can cause failure of the material macroscopically. So one typical example is turbine blades for airplane engines, and you can have catastrophic failures due to the fact that you have these dendrites at the microscale. And so what one would really like to do is to grow alloys and produce alloys where one has a very controlled microstructure. And so our work is starting to give some suggestion of how that can be done.